Inside a fire testing laboratory, a blowtorch roars against a flat plank. The flame licks the surface, blackens it, chars a shallow crater. Then the torch is pulled away, and something strange happens. The plank does not keep burning. No spreading flame, no cascade of orange, no smoke column climbing to the ceiling. The fire simply dies. The material self-extinguishes, leaving a scorched patch and an intact board. To anyone raised on the assumption that wood feeds fire, this looks like a violation of common sense. Yet this is not timber in the traditional sense. It is a composite, engineered in China, built from agricultural fibers and polymers, designed specifically to refuse the things that destroy ordinary wood. It does not rot. It resists moisture and mold. It does not warp in humidity. And in its flame-retardant grades, it earns high fire resistance ratings that natural lumber cannot approach. Around 2018 and 2019, research reports described boards containing as much as 80% plant fiber, bonded without the formaldehyde adhesives that haunt conventional engineered wood. The results traveled fast, and as they traveled, they mutated into a headline that spread across social media and aggregator sites with irresistible force. China has replaced timber with a material that doesn't burn or rot. It is a thrilling sentence. It is also, as stated, false in one crucial word: replaced. That single verb transforms a genuine laboratory achievement into a sweeping claim about the entire global timber economy, an economy of billions of tons, of forests, sawmills, framing crews and furniture factories, built over thousands of years. The gap between what the lab proved and what the headline promised is exactly where this investigation lives. Over the next chapters, we will examine the chemistry, the straw, the polymers, and the missing formaldehyde. We will watch what the material survives. We will decode what a fire resistance rating actually certifies, and we will follow the leap from bench to factory floor and into a 2026 bamboo licensing deal. But first, we must understand what makes wood so precious and so dangerous, and why the world has been hunting for something better for a very long time. Wood built the human world. Before steel, before concrete, before plastic, there was timber. We carved it into boats that crossed oceans, framed it into houses, split it for fires that kept our ancestors alive through freezing nights. Even now, in the 21st century, wood remains foundational. Global roundwood production runs to roughly 4 billion cubic meters every year. Furniture, flooring, roof beams, paper, shipping pallets, chopsticks, matchsticks. The material is everywhere, quiet and load-bearing beneath modern life. But wood carries flaws written into its cells. It is organic, and organic things decay. Left exposed to moisture, timber absorbs water, swells and warps out of true. Fungi colonize it. Rot softens beams until they crumble. Termites and boring insects hollow it from within. And above all, wood burns. Its cellulose and lignin are stored solar energy, chemical fuel waiting for a spark. A dropped candle, a faulty wire, a lightning strike, and a wooden structure becomes an inferno. Whole cities, from London in 1666 to countless timber towns since, have vanished into flame. To fight these weaknesses, we invented engineered wood, plywood, particle board, medium-density fiberboard. These products stretch timber further by gluing chips and veneers together. But the glue introduced a new problem. Many of these adhesives rely on urea formaldehyde resins, and formaldehyde is a recognized carcinogen that slowly off-gases from cheap furniture into the air of bedrooms and offices. Meanwhile, the demand for wood presses on forests. Logging clears carbon-storing woodland, threatens habitats, and in some regions accelerates erosion and biodiversity loss. Each of these failures, flammability, rot, warping, toxic glue, and forest depletion, is a reason to want something better. And China had specific pressures of its own: enormous construction demand, limited domestic forest reserves, and a vast agricultural sector generating mountains of crop residue burned in fields every autumn, choking cities with smoke. The environmental stakes were real, the incentives aligned, and the raw material was already lying in the fields. What if the leftover stalks from harvest could become the beams of the future? That question leads directly into the strange chemistry of turning straw into something like stone. Every autumn, across China's farmland, hundreds of millions of tons of crop residue pile up after harvest. Rice straw, wheat straw, corn stalks, agricultural leftovers traditionally burned in the fields, releasing smoke and carbon and wasting a resource. Researchers looked at these mountains of fiber and saw not garbage but feedstock. The idea behind the composite is deceptively simple. Straw and other plant fibers are rich in cellulose, the same structural molecule that gives wood its strength. If you can bind those fibers together into a solid, dense mass, you can build something wood-like without cutting a single tree. The research reported around 2018 and 2019 described formulations where plant fiber made up as much as 80% of the material by mass. The remaining fraction was polymer, either recycled or conventional plastics, melted and forced into and around the fibers under heat and pressure. As the polymer cools, it hardens into a continuous matrix that locks each strand in place, the way concrete locks aggregate. The result is a fiber-reinforced polymer composite, plant fiber providing stiffness and bulk, plastic providing binding and water resistance. Crucially, this approach sidesteps the formaldehyde problem. Conventional particle board and fiberboard depend on urea formaldehyde resins to hold their chips together, and those resins slowly release carcinogenic gas. Here, the thermoplastic itself is the binder. No formaldehyde adhesive is required, so the finished board does not off-gas that particular toxin. That single distinction gives the material a strong marketing and health advantage over the engineered wood already filling homes worldwide. The chemistry also explains the durability. Because polymer envelops the fibers, water struggles to reach the cellulose, slowing the swelling and rot that plague untreated wood. And by tuning the polymer blend and adding specific compounds, engineers can dial in additional properties, including flame resistance, which we will examine shortly. It is a genuinely clever synthesis. Waste that once fouled the air, transformed into a dense, dimensionally stable panel. But a promising formulation on a laboratory bench must prove itself against the real enemies of wood. So the next question is direct and physical. What, exactly, can this material survive? To trust a building material, you have to torture it. That is what testing does. It simulates decades of abuse in days, subjecting samples to the conditions that destroy ordinary timber and measuring what remains. Start with water, wood's oldest enemy. Natural lumber drinks moisture, swells, and warps. Over years, it splits and rots. The straw polymer composite is submerged, soaked, cycled through, wet and dry. Because the polymer matrix wraps each fiber, liquid struggles to penetrate to the cellulose within. Water absorption stays low. The board holds its shape rather than bloating and cupping. Dimensional stability, the resistance to warping and swelling, is one of the composite's headline advantages. Next comes biology. Rot is not random. It is fungi and microbes feeding on exposed cellulose, breaking down the wood's structure until beams crumble. But the microbes need access and moisture to do their work. Sealed inside plastic, the fibers are far harder to reach. In mold and decay testing, the composite resists the fungal colonization that would riddle untreated wood in the same humid conditions. Termites and boring insects, which chew through timber framing, find the polymer-bound surface far less hospitable than natural grain. Then deformation under load and temperature. Wood creeps, sags, and cracks as it dries or bears weight over years. The composite is designed to hold form under stress, resisting the slow bending and splitting that afflict timber. Manufacturers point to these properties to pitch outdoor decking, where boards face rain, sun, and rot every day. It is important to be precise here. Resistance is not immortality. No material is truly indestructible. Polymers can degrade under sustained ultraviolet exposure, and long-term field data matters as much as lab numbers. But against the core weaknesses that have plagued wood for millennia, moisture, mold, warping, and decay, the composite demonstrably performs better than untreated lumber. And there is one final adversary, the most dramatic of all, the one that opened this film. The torch in the fire testing lab. Ordinary wood burns eagerly, feeding flame with its own cellulose. The composite still contains that same plant fiber, so how does the flame-retardant version refuse to keep burning? To answer that, we have to understand fire itself. Return to the laboratory, to the torch and the plank that would not stay lit. Understanding that moment requires understanding fire as chemistry, not spectacle. Combustion is a chain reaction. Heat breaks down a material, releasing flammable gases. Those gases ignite, producing more heat, which breaks down more material, feeding more gas. Left alone, the loop accelerates. Ordinary wood is a superb participant. Its cellulose readily pyrolyzes into fuel, and the fire sustains itself long after any external spark is gone. The flame-retardant grades of this composite are engineered to break that chain. Manufacturers blend flame-retardant compounds into the polymer matrix. When heat hits the surface, these additives interfere with combustion in several ways. Some release water vapor or non-flammable gases that dilute the fuel. Some form a protective char layer that insulates the material beneath, and some chemically interrupt the reactions that keep flame alive. The result is the behavior we saw. Apply the torch, and the surface chars. Remove the torch, and with no self-sustaining chain reaction, the flame starves and dies. This is what self-extinguishing means. Not fireproof, but unwilling to keep burning on its own. That distinction matters enormously, and it points to what fire resistance ratings actually certify. A high rating is not a promise that a material never chars or never fails. It is a measurement against defined standards, tests of flame spread, of smoke production, of how long a barrier resists fire penetration. Different countries use different systems, and a board that scores well in one test may face different criteria elsewhere. When headlines say a material doesn't burn, the sober truth is more specific. Certain grades resist ignition, limit flame spread, and self-extinguish under test conditions. That is a real, valuable, certifiable property, and it genuinely outperforms untreated timber. But it is not magic, and it is not the same as being immune to fire. The drama of the blowtorch is seductive. The standards behind it are dry, numerical, and precise. Both are true at once. So we have a material that resists water, rot, warping, and flame. The obvious question follows: can it leave the laboratory bench and survive the harsher test of the factory floor and the open market? A laboratory sample is a promise. A factory line is a business. The distance between them is where most breakthroughs quietly die. So the real question isn't whether straw can bond into a plank on a workbench in 2018. It's whether that plank can be pressed by the thousand, priced against timber, and shipped to a construction site without falling apart. Here the Chinese composite crosses a threshold many materials never reach. Extrusion lines and hot press machines already turn agricultural fiber and polymer into finished profiles, cut to length, ready to install. Look at where these boards actually land. Outdoor decking is the obvious frontier because that's where ordinary wood suffers most. A timber deck exposed to rain, sun, and insects begins rotting within years and demands sealing, staining, replacement. A wood plastic composite board shrugs off moisture and needs almost none of that maintenance. Wall panels are a second market, prized because they resist warping in humid climates and arrive in consistent dimensions no natural grain can guarantee. Flooring follows the same logic. Dimensional stability, water resistance, uniform surfaces. These are not hypothetical uses waiting for funding. Wood plastic composites are a real global industry, manufactured across China and sold worldwide, and the high-fiber, formaldehyde-free formulations sit at its ambitious edge. But notice the pattern in that list. Decking, panels, flooring, cladding. These are surfaces, claddings, and secondary components, not the load-bearing beams and structural framing that hold buildings upright. The composite excels precisely where wood is most vulnerable and least critical, in the wet, exposed, decorative zones. That's a genuine commercial position, not a marketing fantasy. It means factories can profit today without waiting for the material to conquer every application. Yet it also draws a quiet boundary around the hype. A product that dominates decking has not replaced the oak rafter or the pine stud. The leap from bench to factory has been made, but it landed in a specific territory, and that territory has edges. To push those edges outward, engineers needed a better raw ingredient, cheaper, more abundant, faster growing than straw. In 2026, they found it in a plant that grows like a weed and produces waste by the mountain. In 2026, a related technology built around bamboo residue was licensed for industrial development, and that single word, licensed, tells a story. Licensing is not a press release or a lab photo. It is a company paying real money for the right to manufacture at scale, betting that a process works and a market exists. It is the sound of an idea leaving the university and entering the economy. Why bamboo? Because bamboo is nearly the perfect feedstock. It is one of the fastest growing plants on Earth, some species surging over a meter in a single day, reaching harvest maturity in 3 to 5 years, while a timber tree needs decades. It regrows from its own root system after cutting, so a bamboo stand isn't destroyed by harvest. It simply sends up new shoots. And crucially, bamboo processing generates enormous quantities of residue. Offcuts, shavings, the dense fibrous scraps left after poles are cut for flooring, chopsticks, and scaffolding. That waste is usually burned or dumped. Turning it into a durable composite means the raw material is not just renewable, but already a byproduct, a cost-negative ingredient waiting to be captured. Bamboo fiber also brings mechanical virtue. Its long, strong strands give tensile strength that rivals some woods and even certain metals by weight, which is why traditional builders have trusted bamboo scaffolding for centuries. Bind those fibers into a polymer matrix, and you inherit that strength while gaining the moisture and rot resistance the composite was designed for. The 2026 licensing signals that developers believe this feedstock can move the technology beyond decking's edges towards stronger, more demanding uses. But signals are not certainties. A license is a bet placed at the starting line, not a trophy at the finish. Industrial development means pilot plants, scaling problems, quality control, and years of production ramp-up before a bamboo residue board reaches ordinary buildings in volume. The direction is genuine and the logic is sound. The timeline is unwritten. Which brings us back to the headline that launched this investigation. The confident claim that China has already replaced natural timber altogether. It is time to hold that sentence up to the light and examine exactly what it gets wrong. China just replaced timber. Read it again, slowly, and the exaggeration reveals itself in 3 words: replaced and already. Everything we have documented is real. The up to -80% fiber content, the formaldehyde-free bonding, the resistance to moisture and mold, the self-extinguishing fire grades, the 2018-2019 research, the 2026 bamboo license. None of it is fabricated, but none of it amounts to timber's funeral. Start with scale. The global timber trade moves billions of cubic meters of wood every year, feeding construction, furniture, paper, and packaging through supply chains centuries old. Composite production, even growing fast, is a fraction of that ocean. To truly replace wood, factories would need to multiply their output by orders of magnitude, an industrial transformation that takes decades, not headlines. Then consider cost. Wood is often cheap, precisely because it grows itself, and the infrastructure to cut and mill it is fully mature. Engineered composites carry the price of polymers, processing energy, and specialized machinery. In many markets, the board still costs more than the plank it means to displace. Consider entrenchment. Building codes, carpenter training, sawmills, hardware inventories, and consumer taste are all built around wood. An industry that does not vanish because a superior material appears. It resists, adapts, and coexists. And consider application limits from the previous chapter. The composite thrives in decking, cladding, and panels, not yet in the structural bones of buildings where solid and engineered timber still reign. So the honest verdict weighs genuine promise against stubborn reality. The promise is substantial, a rot-proof, fire-resistant, waste-derived material that solves wood's worst weaknesses in exactly the places wood fails most. The reality is that promise operates within boundaries of scale, cost, and tradition that no laboratory result erases. This is how technology actually advances, not by one triumphant substitution, but by a new option carving out territory, year by year, use by use, which leaves us with the final task: separating cleanly what has been proven from what has been hyped, and naming honestly where this material is truly headed. Let us separate the material from the myth one last time, cleanly, so nothing false survives the closing frame. What is proven? Agricultural and bamboo fibers can form up to 80% of a durable composite. That composite can skip the formaldehyde adhesives that haunt conventional engineered wood. It resists moisture, mold, warping, and decay. Flame-retardant grades earn high fire resistance ratings and self-extinguish once the flame is pulled away, the very plank that opened this film refusing to keep burning. It is manufactured today into decking, flooring, wall panels, and cladding sold around the world. And in 2026, a bamboo-residue process was licensed for real industrial development, pointing towards stronger feedstocks and wider uses. All of that is solid ground. Now the myth. That timber has been replaced. That forests are obsolete. That a single Chinese material has ended humanity's oldest partnership with wood. These claims collapse under the weight of scale, cost, application limits, and an entrenched global industry that will not surrender in a headline's lifetime. The composite has not conquered the structural beam, the framing stud, the vast cheap ubiquity of ordinary lumber. It has instead done something more modest and more honest. It has become an excellent answer to wood-specific failures, in the wet and exposed places where wood rots and burns. Where, then, is this technology realistically headed? Toward growth, not conquest. Toward decks that never rot, panels that never warp, claddings that self-extinguish, built increasingly from crop straw and bamboo scraps that would otherwise be burned as waste. Toward a future where composites and timber share the built world rather than one erasing the other. That is not a lesser story. Turning agricultural residue into fire-resistant building material is a genuine achievement worth celebrating as long as we celebrate the right thing. So hold both truths at once. The innovation is real, and the replacement is not. The lab result is impressive, and the funeral is fiction. Remember what this material actually is, and remember what it isn't. It is a promising material, not timber's funeral.